So, hello students. Today we are going to start with our next chapter, that is the electrostatic fields. So, firstly, what is the meaning of this electrostatic fields? Here, the electro means electric fields, okay, and static means that are stationary, that are static, that are steady, okay, that is not vary with time, जो कि time के साथ vary नहीं हो रहे हैं, ठीक है, time के साथ as the time moves on they are still. Okay, so that's why these are the electrostatic fields. And before starting with the actual concepts, so we have to study some of the definitions first in this. So electrostatic fields are the fields which do not vary with time, which do not vary with time. So that these are the electrostatic fields. And before starting with actual concepts like the insertion of del, gradient, divergence in this chapter, so there are some terms that you have already studied in your previous classes. So that is like Coulomb's law is there. Okay, electric charges are there, dipole is there, equipotential surfaces are there. So that type of concepts we have to study first, some basic concepts related to these electrostatic fields. So starting with the first one is the charge distribution. That what is the concepts behind the charge distribution? Okay, so the charge distribution, there are three types of charge distribution. The first one is linear charge distribution. Then the second is the surface charge distribution. And the third one is volume charge distribution. Okay, so as per the dimensionality of the problem, so there is linear charge distribution, there is surface charge distribution, and there is the volume charge distribution. Now for the linear charge distribution first, its symbol is lambda. Okay, its symbol is lambda, and the formula it is dq by dl. Okay, so what does this meaning actually? Linear charge distribution, that charge is distributed linearly over a straight line or some curve. Okay, when the charge is distributed over some curve or a straight line, then we said that it is a linear charge distribution, and it is represented by lambda and dq by dl, where q is the charge and l is the our line, length of the line. Okay, so it is dq by dl. So, and now what are the units for this lambda? Units for charge is coulomb, and the unit for length is meter. Okay, so the unit for this is coulomb per meter. Okay, this one is the linear charge distribution. And similarly, for the surface charge distribution, the symbol is sigma, and this is equals to dq by ds. S here represents your two-dimensional surface. Okay, and for this, the units are, the unit for charge is coulomb, and for the unit for surface is meter square. Okay, so here comes out to be coulomb per meter square. So that means when the charge is uniformly distributed over any two-dimensional surface, so that we called as the surface charge distribution. When the charge is uniformly distributed over any two-dimensional surface, any surface of any type, any shape. Okay. Third one is the volume charge distribution. Okay, and the for volume charge distribution, the symbol is rho, and here the formula is dq by dv. dq by dv. And here the units are Coulomb per meter cube. Okay, so these are the units for volume charge distribution. That means when the charge is uniformly distributed over any volume. Okay, charge is uniformly distributed over any volume. So it is called as the volume charge distribution with the units Coulomb per meter cube. Okay, so this is the charge distribution which is of three types. Now the next concept is the Coulomb's law that you have already studied in your physics class. So Coulomb's law. Now, what is Coulomb's law? So it states that the force of interaction between the two stationary point charges. Okay, the force of interaction between two stationary point charges, let us say Q1 and Q2, is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. So this is your Coulomb's law. So mathematically it can be written as it is the force of interaction between two charges, any two charges. Let us say here it is Q1 and here the charge is Q2 and the distance between them is R. So the force of interaction between the two charges Q1 and Q2, this is directly proportional to the product of the charges. That means this force is directly proportional to Q1, Q2, and it is inversely proportional to the square of the distance between these two charges. Okay, that means it is inversely proportional to the R square. Okay, and collectively it can be written as, so it can be written as F is directly proportional to Q1 Q2 by R square. So it can be written like this. Okay, and if we are going to remove this proportionality sign, so it can be written as, therefore, after removing this proportionality sign, so it can be written as F is equal to 1 upon 4 pi epsilon naught Q1 Q2 by R square. So this is the formula of the force of interaction between the two charges Q1 and Q2. Okay, it is 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, and we know the units for force is Newton. The unit for the force is Newton. And what is epsilon naught? It is called as the permittivity. Okay, here epsilon naught is called as the permittivity of free space or vacuum. Okay, epsilon naught, this is called as permittivity of free space or vacuum. Okay, and what is the value of this permittivity? It is 8.854. It is equal to 8.854 into 10 raised to power minus 12. Okay, it is 8.854 into 10 raised to power minus 12 with the units Coulomb square per Newton meter square. Units are Coulomb square per Newton meter square. You must know this value 8.854 into 10 raised to power minus 12 for permittivity. And what is the value of this complete proportionality constant? That is 1 upon 4 pi epsilon naught. If you solve this now with epsilon naught as 8.854 into 10 raised to power minus 12, so this comes out to be 9 into 10 raised to power 9. Okay, 1 by 4 pi epsilon naught is equals to 9 into 10 raised to power 9 with the units Newton meter square per Coulomb square. ठीक है, Newton is for the force, meter square is for the r square, and Coulomb square is for the q1 q2. Okay, the units for charge is Coulomb, the units for distance is meter, and for the force it is Newton. Okay, so it comes out to be Newton meter square per Coulomb square. And one thing to note down here that as here we are considering there are two charges q1 and q2, and if we have to consider that the force of interaction of q1 over q2, then we write this as F12, and this force is a vector quantity. Okay, it sees the direction. This force is a vector quantity. F12 represents the force exerted by charge 1 over the charge 2. Okay, and if you written here that F21, so that means the force exerted by charge 2 over the charge 1. Okay, and these two forces are not equal. They are opposite in polarity to each other. Okay, so F12 is equal to negative of F21. So that means this force is a vector quantity. It sees the direction. It has magnitude as well as direction. So this is all about the Coulomb's law. So before starting with the actual terms, so we must deal some basic terms we must know, like permittivity. So there are some numericals where you have to use these values directly, like permittivity, that is 8.854 into 10 raised to power minus 12, or 4 pi epsilon, 1 by 4 pi epsilon naught is equals to 9 into 10 raised to power 9 Newton meter square per Coulomb square. So that these values, you must remember these values. Now the next one is, so here this one is the electrical force. Now next is the electric field intensity. Next term, electric field intensity. Electric field intensity, it is again a vector quantity and it's represented by E vector, and this is defined as the force per unit charge. Okay, this is defined as force per unit charge. This is electric field intensity, or you can further write it as 1 by 4 pi epsilon naught Q by R square. There is a single charge Q by R square. So simply you written here Q instead of Q1 and Q2. And now what are the units? It is force per unit charge. So it can be, the units can be Newton per Coulomb. Okay, Newton per Coulomb. So these are the units for electric field intensity. Okay, now the next is the electrical lines of force. Next is that you must know, that is the electric lines of force, or sometimes we said that the electric field lines. Electric field lines. Electric lines of force or electric field lines. Like now, for the positive charge, the lines are in the outward direction, like this. That means the electric field lines coming out from the positive charge. And for the negative charge, like this, the lines have inward direction. So that means for the negative charge, the lines, electric field lines are directed inwards. Okay. And if there is some dipole of the combination of positive and negative charges, so the electric field lines can be drawn like this. From the positive charge, they are outward direction, and towards the negative charge, like this. For the negative charge, they have inward direction. So these are the directions for the electric field lines. Okay, and this type of arrangement where the positive and negative charge is there, so this we called as the dipole. This called as the electric dipole. That means, what is electric dipole? It is a pair of equal and opposite point charges separated by some small distance. Okay, that is the electric dipole. What is dipole? It is the pair of equal and opposite point charges. They are equal, but they have the opposite polarity, but and separated by some small distance. So this is called as electric dipole. And what is the formula for the dipole moment? Yes, dipole moment is, we can simply write the formula for the dipole moment as it is, the symbol is P, it is Q into 2A. We generally write the formula like this. Okay, Q into 2A. Q is the charge, magnitude of the charge. Okay, because the magnitude of both the charges is equal, but their polarity is opposite. Okay, so simply we write here Q into 2A. 2A is the distance between that two charges of opposite polarity. Okay, and so from this formula, the unit comes out to be Coulomb meter. Okay, unit is Coulomb meter for the dipole moment. Okay, and after that, the next concept, first of all, we have done the force, then electric field intensity, then electric lines of force, then dipole moment, and now next is the electric potential. Electric potential. Okay, electric potential, it is the amount of work done in moving a unit positive charge from infinity to that point against the electric force of field. Okay. So what is electric potential? Electric potential means it is the work done. How much work done is done for moving a charge from infinity to any point in the region of electric field lines. So that is called as electric potential. Okay, and simply we write the formula for the electric potential as V is equals to W upon Q. Okay, that is the work done per unit charge. That how much work is done in moving the unit charge from infinity, from any point in the infinity to the point in the region of electric field lines. And the units for the potential, we all know that it is volts. This is the unit for potential. And also there is one more definition for electric potential, that it is defined as the negative of line integral of electric field intensity from infinity to that point. That means there is one more definition, that it is the negative of line integral of electric field intensity. This one, negative of line integral of electric field intensity in moving the unit charge from infinity to any point from infinity to any point, say A. Okay, where A is any point in the region of field lines, any point in the region of electric field lines. That is how much work is done in moving that charge. So it is also given by this formula or by this formula, that is the negative of electric field intensity from infinity to any point A. Okay, now next one is after electric potential, there is the potential difference. Okay, now what is the difference between simple electric potential and potential difference? That in the case of electric potential, we are moving the charge from infinity to any point in the region of electric field lines. But in case of electric potential difference, we are moving the charge between the 2 points. Say one point is A and another point is B. So how much work is done in moving the charge from point A to point B? So that is the potential difference. Okay. So the next one is electric potential difference. Electric potential difference. Okay, it is defined as when moving it is defined as the amount of work done in moving a unit positive charge from one point to other point in the region of electric field lines. Okay, in moving the charge from one point to the other point in the region of electric field lines. So if there are 2 points, say one point is A point, another point is B in the region of electric field lines. So what is the work done in moving the charge from point B to point A? Okay, or what is the work done in moving the charge from point A to point B? Okay, so for this, the formula can be written as like VB minus VA. So that's why it is called as electric potential difference. Okay, VB minus VA is equals to WAB, that is the work done per unit charge. Okay, VB minus VA is equals to WAB by Q naught. Or in the form of integration, so this can also be written as negative integration, line integral of this electric field intensity from A to B, when we have to move the charge from the point A to the point B. Okay, so this one is your electric potential difference. Okay, and there is one more formula we are very much familiar with the electric potential difference, is that one more formula the same as the formula of force. The force is 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, and then electric field intensity is 1 by 4 pi epsilon naught Q by R square. Okay, so similar formula for electric potential is, it is 1 by 4 pi epsilon naught Q by R. Okay, and here R is the distance between the 2 points. Okay, there is one more formula, that is 1 by 4 pi epsilon naught Q by R, and here also epsilon naught is the permittivity, and the value for this complete constant 1 by 4 pi epsilon naught is 9 into 10 raised to power 9. Okay, so this one is the potential. Now next one is one more basic concept, that is the equipotential surfaces. Very important. Next is equipotential surfaces. Equipotential surfaces. As from the name, it's easy to guess that what is there. It has those surfaces, those two-dimensional surfaces where the potential is same. Okay, on the whole surface where the potential is same. So let us suppose, like if there is any surface S, okay, and this is an equipotential surface. So for the equipotential surface having the this surface has same potential everywhere, same potential everywhere. So what is the work done now in moving the charge within the equipotential surface? So what is the work done in moving the charge? Let us suppose my charge is at, this is point A and here it is any point B. Okay, and I have to move the charge within this equipotential surface from point A to point B. Okay, so what is the work done? As this surface has equal potential, okay, that means potential at location A is equal to the potential at location B. So see this formula, see this. Okay, VB minus VA, this comes out to be 0. So the work done comes out to be 0. Hence, in case of equipotential surfaces, the work done is 0 when we have to move the charge from one location to the other location within the equipotential surface. Okay, so for the equipotential surface, VA minus VB, or you can also write VB minus VA, okay, is equal to 0. Okay, because the potentials are same over the equipotential surface. Therefore, WAB is equal to 0. Okay, hence, in case of equipotential surfaces, the work done in moving the charge from any point A to any point B is 0 because the potentials are same everywhere in case of the equipotential surfaces. Okay, so these are some of the basic concepts that you must know before starting with the actual chapter of electrostatic fields, in which we have to again deal with the del, gradient, divergence concepts. Okay, so these are some of the basic definitions that you must remember. Okay, so the next topic is potential gradient. Okay, and as we know that what is gradient, we have covered in our basic chapter. So gradient is the product of del with any scalar. Okay, and from the last some definitions, we have also observed that force is a vector quantity. Okay, electric field intensity is also vector quantity, but the potential is a scalar. Okay, potential is a scalar, and here the gradient is taken of this potential, and what is the result? That is all what we have to derive in this derivation. So we have to take the potential, that means simply we have to do del V. Okay, so in the case of gradient, there is no dot product, there is no cross product. It is the simple multiplication of any scalar with del function. So this is called as the potential gradient. And in this topic, we have to prove that, to prove E is equal to minus del V. ये रिजल्ट निकल के आएगा जब हम इसका प्रूफ करेंगे. ठीक है, E is vector quantity, and when you take the gradient of any scalar quantity, that will gives you a vector quantity. Okay, so from this, the result comes out to be that E is electric field intensity. Okay, now we have to apply all the concepts of del, gradient, divergence in the terms of electric fields. Okay, so minus del V is equal to E vector. E is electric field intensity. Now let's start with the proof. Yes, consider any 2 points A and point B with the potentials, a small change of potential between the 2 points. Let us suppose here is the point A and here it is the point B, and the coordinates for point A are X, Y, Z. These are the points in the three-dimensional space. Okay, so that's why their coordinates are some coordinate of X, some coordinate of Y, and some of Z also. Okay, and similarly for the coordinates for B are X plus delta X. It can be written as delta X or dx. Okay, dx means the small change. If here X is 1, then dx बीच में 0.5 या you can add 0.01. A small dimension is added to the original dimension. So that is dx. X plus dx, y plus dy, and z plus dz. Okay, these are the coordinates for this point B. Okay, and let us say the potential at point A is V. The potential at point A, there is one point and here it is another point. Here it is V. Then the potential at point B is V plus dV. Okay, so these are some of the assumptions that we have to assume before starting the proof. Let us suppose there are 2 points A and B with the coordinates x, y, z, and for point B it is x plus dx, y plus dy, and z plus dz, and their corresponding potentials are V and V plus dV. And let us say the distance between the 2 points is dr. It's a small distance between the 2 points, and this dr is a vector quantity and it is represented like, so dr is a vector quantity, a small change in the distance. Okay, so it can be written as dx I cap, because it is a vector quantity and it can be written in the terms of unit vectors. Some unit vector for I, j, and k. Okay, in the three-dimensional space. It can be written as dx I cap plus dy j cap plus dz k cap. See here, here is the x, y, z, and here is x plus dx, y plus dy, and z plus dz. And if you get the difference between these 2 points, so that will gives you the dr, and that difference is just dx, dy, and dz. So that's why we are going to write this dr vector like this: dx I cap, dy j cap, and dz k cap. This is for the dr vector. And also the potential difference between points A and B. The potential difference between points A and B can be written as dV. Okay, see here, the potential here it is V. Here the potential is V plus dV. So what is the difference between the two potentials? So that is dV only. Okay, and this can also be written as the potential is a scalar quantity. Okay, so this can be written as in the form of partial derivatives. So it can be written in the form of partial derivatives like this: curly V by curly X dx, okay, plus curly V by curly Y dy plus curly V by curly X dx. Okay, mark this as equation number 1 and this as equation number 2. And I have already said that potential is a scalar quantity, and so there are no unit vectors in this formula. So it is simply written in the form of partial derivatives for the 3 dimensions x, y, and z. Okay, so and also we know that from the previous formula of potential, that potential is also equal to the negative of line integral of electric field intensity. Okay, that we know. Potential is the negative of line integral of electric field intensity. But here is not the complete potential. Here is dV. So this is also equals to minus E dr. Okay, so that line here we indicate that line, that difference with dr. So this is also equal to this. Okay, you can also give the reason for this concept, that because potential is also equal to minus of E dl. Okay, and here in this formula we are taking dV. Okay, so that's why we have not put here the integration sign. Okay, so it can be written as minus E dot dr, and just mark this as equation number 3. Okay, and in the next also, now what is E vector? So E is a vector quantity. So this can also be defined in the terms of unit vectors. Okay, so this can also be defined in the terms of unit vectors, and so that's why it can be written as in the form of x, y, and z components. So Ex I cap plus Ey j cap plus Ez k cap. Okay, so it can be written like this: Ex I cap plus Ey j cap plus Ez k cap. Now mark this as equation number 4. Okay, and now in the next step, put 4 and 1 in 3. Put 4 and 1 in 3. So in the next step, put 4 and 1 in this equation, that is the equation number 3. So this will gives you I'm just going to rub it. So when you put down the equation number 4 and equation number 1 in this equation number 3, so this will gives you dV is equals to minus of what is E vector. E vector is this much, that is Ex I cap plus Ey j cap plus Ez k cap dot dr. Okay, dr is this one, that is dx I cap plus dy j cap plus dz k cap. Okay, and now there is the dot product between the two terms. So this will gives you as a output the scalar quantity. So scale in the dot product, you directly multiply I dot I, j dot j, and k dot k, because the rest of the terms, that is I dot j or I dot k, are all 0 due to the 90-degree angle between them. Okay, so it can simply be written as minus of Ex dx plus EY dy plus EZ dz. Okay, so this is the answer for dV, and just write it as equation number 5. Okay, writing it as equation number 5. Now, in the next step, compare 5 and 2. Okay, in the next step, comparing equation number 5 and equation number 2. Comparing 5 and 2. Okay, this equation number 5 is also equal to dV, and this equation number 2 is also equal to dV. And when you compare them, so here it is dx, here is also dx. Here it is dy, here it is dy, here it is dz, here it is dz. And from this comparison, so what do we notice that ex, this is equal to, or you can also write negative of ex is equals to curly v by curly x. Okay, but I am going to write down here as ex is equals to minus curly v by curly x. Okay, after this comparison of equation number 5 and equation number 2, and ey is equals to minus curly v by curly y. And similarly, Ez is equal to, when you compare this with this, it is minus curly v by curly z. Okay, this comes out after the comparison of equation number 5 and equation number 2. Okay, so in the next step, again rewrite for the E vector now. Again, we are going to write the E vector, that is the equation number 4. Therefore, this E vector now again can be written as, so here it is Ex I cap, and what is Ex? Minus curly V by curly X. Okay, Ey j cap, so what is Ey? This much. So simply I can write it as, I am taking the negative sign out, and curly V by curly X I cap plus, instead of Ey, I am going to write down here curly V by curly Y j cap plus, and instead of Ez, I am going to write down this, that is curly V by curly Z k cap. This much. Okay, and the negative sign that are here, I am taken that negative sign out. Okay, so now this can also be written as taking V common. Okay, take the V common. Now taking this scalar quantity V common, so it can be written as curly by curly X I cap plus curly by curly Y j cap plus curly by curly Z k cap, and take V out. Okay, from this equation. And what is this? That is curly by curly X I cap, curly by curly Y j cap. This represents your del. Okay, so this comes out to be minus del V, hence proved. Okay, so this is the complete proof for the topic of potential gradient. That is E is equals to minus del V. Hence, proved. Now let's do one numerical related to the concept of potential gradient. So the numerical is to calculate E vector at the coordinates 14, 16 if V is equals to 10y cube plus 20x square. Okay, so we know that V is a scalar quantity, so no I, j, k unit vectors are there. So for this, we have to use the concept of potential gradient that we have derived recently. So like as per that formula is E vector is equals to minus del V. That is, you have to take the gradient of this potential function. Okay, so you have to simply do the gradient of this. So what is del? It is curly by curly x I cap plus curly by curly y j cap plus curly by curly z k cap. This is del. And V, it is given in the question. It is 10y cube plus 20x square. Okay, this is V. So you have to do the calculation for minus like curly by curly x of this. It is 10y cube plus 20x square. Okay, and I cap plus curly by curly y of again 10y cube plus 20x square j cap plus, now no need to do this with the curly by curly z because there is no z term in the function given for the potential. There is no z term, there is only x term and y term is there. So when you do the partial differentiation with respect to z, so this will automatically gives you the zero answer. Okay, so directly write down here as 0. Okay, now simply solve these partial derivatives and finally put down for x equal to 14 and for y equal to 16. Okay, so in this numerical, after this, simply take the partial derivative for this. So this comes out to be 40x. So 22 is a 40x I cap plus 30y square for this term j cap, and for the k it is 0. So now just put down the values of x and y as it is given in the question 14 and 16. So 40 into 14 I cap minus 30 into 16 square j cap. So this is the final answer, that is minus 560 I cap minus 7680 j cap. So this is the final answer for this numerical, and that is related to the concept of potential gradient. So this is all for today's lecture. Thank you.